Welcome to Wireless LAN Weekly, a podcast focused on the wireless networking professional. We aim to educate, inform, entertain, and inspire. Get ready to listen and enjoy. Now to our host of the show, Keith Parsons.
Hello again. This is Keith Parsons, your host of Wireless LAN Weekly. Glad you could join us back again with episode 25. In today's episode, we have a tech section with Matt Holdrege. Matt's been a longtime technologist and worked as a CTO and a whole bunch of other highly technical jobs as a career. He's currently living in France, but he's an American citizen. We're glad to have Matt with us today, and he'll be talking to us a bit about mesh networking, as well as a new bit of antenna technology that I found very intriguing. So let's get on with the show.
Things every wireless LAN professional needs to know. Gear up, buckle down, and stand by for the real techie stuff.
Well, welcome back. This is Keith Parsons, your host of Wireless LAN Weekly. And in this week's episode, our technology section is with Matt Holdrege. Matt Holdrege is going to be talking to us today about mesh networking and new antenna technologies. Matt's got a very wide and varied technical background, and we're glad he can join us. He's talking to us today from France. So welcome, Matt.
Hello, Keith. Thanks for having me.
So I'm in Utah, and you're in France, and we're having a discussion, and someone's going to pick this up on their iPod or iPhone, and they'll be running on a treadmill in a whole other place of the world. Kind of a great world we live in today.
We're very fortunate to have the global networking at our fingertips.
It does make it very easy. So I'll just let you get started on mesh and antenna technologies. I'm kind of interested in what you've got to say. You'd responded to a tweet I'd put up on Twitter about 2.4, and I said it's kind of over, as in it's very oversaturated, and you responded with maybe not quite yet. So I'm interested in what you got to say there. So go ahead and take it away.
Sure, Keith. I'm talking about new generations of Wi-Fi, and we've been talking about this for a number of years, that, you know, Wi-Fi started out as a very simple concept, a radio chip connected to an antenna with a little power, and that's all there was to it. And we say that's the first generation of Wi-Fi. Now, unfortunately, that developed into a broad consumer market, and that's what everybody thinks Wi-Fi is. And in reality, there's several other generations of more professional systems that use the 802.11 Wi-Fi protocol that can do so much more than the average simple access point that we all know and love. But I try to say that this is not your father's Wi-Fi that we're talking about here. This is the second generation, I call, is more the access controllers. That where you had a centralized controller that controlled lots of dumb access points, like the airspace, which was acquired by Cisco, and Aruba does that sort of thing. And then the third generation is a wireless mesh, where the access points, or wireless nodes as we call them, operate independently and intelligently, and in fact have no wires themselves. They are unwired. They sit out in the network somewhere without any wires connected to them, and ideally have multiple radios to backhaul back to wherever the wire is, and to receive other backhaul traffic and pass that on. And so mesh networking came about to solve that problem, to reduce the number of wires in the network, to make it manageable, and to make it work in an outdoor network across the city. As we called it a few years ago, municipal Wi-Fi, that became quite popular, but never really took off for a few reasons I'll go into. But there were several generations of mesh networking. The first generation is single radio, where everything was happening on one radio, where both the access and the backhaul. And obviously that's kind of limiting when you scale up the performance and use real-time applications such as voice over IP or video conferencing or video surveillance, these kinds of things, even video streaming. So some companies came up with a second radio using 5 gigahertz for the backhaul, which makes a lot of sense. It offloads all the traffic, the backhaul traffic from the 2.4 spectrum, and lets it the 2.4 focus on the access, since at least a few years ago, 90% of all the clients were 2.4 and not so much 5 gigahertz. It's getting a little better now, but it's still our iPhones and these kind of devices all use 2.4. So the third generation said that okay, the two radio is good, but since there's only one backhaul radio in every wireless node, that means they're all using the same channel. They all have to be obviously using the same channel to talk to each other. And so since wireless, since 802.11 is a CSMA technology, carrier sense multi-access, that means only one can send at a time, and we stop and listen for the opportunity to send another packet. And if all these nodes are using the same channel, they're sharing the same CSMA space. And obviously, as the utilization ramps up and real-time packet applications need access to the channel and can't get it all the time, it's going to suffer. So finally, we have the newest generation of wireless mesh, which is multiple radios, where each hop, as we call it, each wireless hop to the network is on a separate spectrum, on a separate pair of radios, and consequently a separate CSMA domain. So there's only two entities using that channel, and they can get the good usable throughput between the 2 points to really have a good usable backhaul network.
That leads to a question. If there's multiple radios and each little mesh hop is one frequency, which I love, and I think it's a great idea, because that collision domain thing's the bugaboo of all wireless, is how many radios do you need in a mesh radio in order to maintain multiple links?
Yeah, so what Strict Systems decide, and that's one of the companies I represent here, decided to do is create a radio board with two radio chips on it, a 2.4 and a 5 gigahertz, and put it in a chassis where you can slide them in and slide them out, and put up to 3 of these modules inside of a wireless node. So you have up to 6 radios, 3 2.4 gigahertz, 3 5 gigahertz. So one of the 5 gigahertz radios is dedicated to backhaul, which is sending the traffic back to wherever the wire is. And so it's operating as an 802.11 station. And it's connecting to another radio somewhere in the network that's, of course, an access point. And in general, we're talking about 5 gigahertz, although it's flexible to do 2.4 or even 4.9 in public safety apps. But so you would have one of those radios doing the backhaul and the other two listening to receive other mesh nodes further out in the network. And obviously, this makes sense in larger networks. In small, tiny networks, you don't need this much. And the other value was, and this is going back several years when this first started, was having 3 2.4 gigahertz radios and making use of sector antennas. And what we found in the earlier days of Wi-Fi is all these access points used omni stick antennas. And omni stick antennas are very simple devices that they can receive obviously at 360 degrees. And what the problem is, though, is they receive noise at 360 degrees. And also you are limiting yourself to one radio serving a population of an area where you may end up needing more radios if it's a dense area of users. So the going to the sector and 3 radios serving one area with 3 sector antennas, each 120 degrees was common. You triple the number of users you can support, and each of these sector antennas is limiting itself to the amount of noise that it is sending down to the radio. And in Wi-Fi, what each radio does is it samples the preamble of a packet and rejects it if it's not intended for it. If it's not a fully formed packet, or if it's maybe for another access point or something, it rejects it. And even if it is intended for that radio, it may be out of sequence with the packet flow or maybe an incomplete packet and has to ask for a retransmit. So your average Wi-Fi radio is sampling a lot of packets and rejecting, and then accepting the one good one it gets out of the bunch if there's a high noise ratio. The signal-to-noise ratio is not good, in other words. So that was some of the immediate benefits we bought by having these multiple radios. We get great performance as we hop wirelessly through the network, so we don't drop bandwidth off. And that was a complaint of earlier mesh networking that had 1 or 2 radios, is that for every wireless hop, you reduce the bandwidth by a certain percentage. And of course, you up the latency in the case, which is important in the case of voice over IP, where we're sending out speech frames every 20 milliseconds, and if you miss a few of those frames, then the quality diminishes. So by moving to a node that contain up to 6 radios, and by the way, it's 2, 4, or 6, so it's not every node that needs the 6 radios, but it's inside one simple box that can be placed in a fully weatherproof outdoor container and used anywhere in the world, and is used everywhere in the world, from the mountains in Russia and Finland into the deserts of Phoenix and Saudi Arabia. So this is definitely a all weatherproof system. And we now have a system that can scale to large networks. And another very important factor is this is layer 2 networking. These are Ethernet switches in the sky, as we call them. And that's key for integrating into large networks that maybe use MPLS core networks and VLAN management of their customer networks. That it integrates perfectly with that, because we can pass the VLAN tags right through the layer 2 wireless network, and it comes out the other end with the same VLAN tag and the same control and management that is applied, and quality of service that is applied throughout the rest of the core network. And it also, the other value of mesh, and I'll take a step back and say, we all owe a lot to the U.S. Department of Defense for creating mesh networking, because it led to the Internet. The Internet is a mesh network, in other words. And the Internet was designed by the Defense Advanced Research Projects Agency to survive battlefield conditions. And what that means is if any one part of the Internet is destroyed by a missile, the rest of the Internet survives. And we know this to be true today. So the same concept is applied to mesh networking, so that if any one part of this network goes down, and it could be a power issue, it could be an antenna issue, it could be a tree blowing in the wind that affects the traffic, or a big truck driving by that blocks an antenna. Any of these things happen, and the mesh survives, and it reroutes instantly. Now, we know in Internet networking, a reroute can involve a route convergence, which can take a long time at layer 3. But in layer 2, it's instant, because inside it's in an Ethernet switch model, it's the same thing. We change paths from one switch port to another in just a few milliseconds. And it's the same concept with wireless mesh. We rebuild the mesh in a matter of milliseconds. And the way that works is each of these mesh nodes is aware of its secondary and its tertiary potential paths in the network. And it's just a simple flip a switch in memory to have it go from one to the other. And another side benefit from this, which nobody thought about at the time, was this allows mobility to work. And sure enough, we've got this mesh networking running on high-speed trains. We've even tested it up over 300 kilometers an hour, or over 200 miles an hour. Wi-Fi at multi-megabits per second, and most people kind of shocked when they hear that. And it's absolutely a non-standard, because there's no IEEE standard yet for doing this, but it uses the 802.11 technology. It simply adds a few bits into some beacons, the 802.11 beacons, which gives the hints needed for the nodes to know what their secondary and tertiary paths could be if the link breaks. And so in a mobile situation, your link breaks when you move away from the access point, but it can reheal when you come to the next one. And so that's why with the performance capabilities put in by Strict Systems, that's what allows high-speed Wi-Fi to work in police cars and trains and ambulances and fire engines. And that's one of the key parts for municipal Wi-Fi to have a business model in a city, is to allow multiple users, including the government, emergency response services, as well as regular users, and businesses to use the same infrastructure, and effectively resell the network over and over and over again, which ultimately pays for it. I know the old business models of that Philadelphia and San Francisco and New York tried to do several years ago, didn't really include all this, and they were talking about free Wi-Fi, and that business model failed. So those big city network projects all failed, and they were doomed by politics as well. So we're having a lot of success with smaller cities that do employ this model, and using the reserving bandwidth for the police and the emergency response systems, as well as being able to sell the network to various other anchor tenants, universities, banks, and things like that, and other non-emergency aspects of the government and the general public.
Well, that leads a question. You're going to back up just a little bit. As you mentioned, the unique adding a couple of bits into a beacon. I can understand how the mesh-to-mesh nodes can use this extra little piece of information. What about the client access level? Do they also understand what's going on in that beacon, that extra pieces that are being added there? I'm sure they're in the proprietary format.
Yes, since they are proprietary, it's not part of a standard. That means your laptops and your BlackBerries and iPhones, of course, aren't going to understand these messages, but it doesn't cause them any problem. It's just inside this. It is standard because it's inside a standard field of the 802.11 beacon, but it's not going to be readable or interpretable by a client that isn't programmed to interpret it because it's in a vendor-specific area.
Well, CCX does the exact same thing, so yeah, we understand how that works. But is it possible to get clients that understand those by reprogramming those?
Oh, yeah, sure. It's a very simple thing. But let's look at where is it important, and we put it into our products to make first of all to make mesh networking work, and secondly to enable high speed networking. Now, in experience, we found that ordinary 802.11 works fine at walking and speeds and very 10 mile an hour driving speeds. You don't even need these extra bits because the client device driver in your laptop or your iPhone can see the next access point at the same SSID. And obviously, it's got to be in the same IP subnet, so there's no DHCP going to happen as you do the roaming. It's just a simple switch, and it actually works at slow speeds. It's when you get to higher speeds that these clients need some help. And so, if there's a need for that, sure, it's certainly possible. But I don't want to talk out of school, but this has been IEEE standard for doing roaming has been worked on for many, many years now, and it hasn't really gone anywhere. I stopped following it myself a while ago. I don't know the current status, but it's a belief by a lot of people that the mobile operators didn't want it to succeed because they were betting their bank on 3G, and they didn't want Wi-Fi to be able to work really well in a mobile scenario. So whatever the case is, we don't have a real significant standard today to do this, and so we have to do it in a proprietary sense.
What? You're saying the IEEE might have politics involved?
Yeah, it's all standards groups do, and that's
my heart beats
still. I've worked with the IEEE and IETF, and ITU involves, when you work at the ITU, you're doing national politics, and it's China versus America and England versus France, and it's pretty amazing things that happen there in Geneva. But we down at the user level, we have to work with whatever is given to us, and so in the case of Strict Systems, they had to engineer their own solution to make wireless mesh work in a high performance manner, and that's what we're left with today.
Well, as a technologist who's been around the block, so to speak, for a long time in this, what's Gen 4 going to be then?
Well, first of all, it's a marketing name. 4G is just
no, not 4G. You had said the first generation was autonomous APs, the second was controller, the third's mesh. I was just wondering if you're already, being a futurist here and looking at what the fourth generation wireless is going to look like.
I don't see anything like a fourth generation in the infrastructure sense, but if we want to add more intelligent networking to the client, that you could call that a 4G, where the client, as we're starting to allude to, can participate in the intelligent mesh instead of just being at the edge of it. So that could be very interesting if we can get all the vendor groups to agree on how that's going to work.
Yeah, that's the big trouble here is all on the client side. Devin Aiken had put a tweet up a couple days ago that said if you have 49 clients per AP, 98% of your wireless problem is the client. And I responded with, if you just have 10 clients per AP, 90% of your problem is still the client. We got to get the client side fixed. So, well, you talked about mesh. How about you mentioned you have some information on new antennas as well?
Yeah. One more quick thing to say about the radio side, though, to your point you just made. You can also engineer the radio chip better and tweak the retransmission schemes better so that you can load up a lot more clients onto an access point. And these strict access points support up to 128 associations per radio. Now, if you actually had 128 power users, of course, it'd be slow as mud. But when you consider that oversubscription ratios, and you may actually only have 30, 35, 40 people using it, even though 120 are connected, then it does scale. And we've done tests with independent labs where they've had 35 voice over IP associations all talking at the same time, working on one access point. So it is possible to have high performance access points that can handle a large amount of users.
And not just in the theoretical sense that we can handle 128, but you can actually handle the conversation load.
Yeah, these radios can accept and do accept 128 802.11 associations at one time. They can all be 128 clients can be associated to one radio, and you have to assume that not all those 128 are going to be powering away at their PCs and doing downloads and phone calls at the same time. And in a real world situation, that is the case, and it's the same with DSL. Phone companies figure in oversubscription ratios when they build their DSL networks and assume that not every house is cranking out the packets at the same time. But when we do load up, like I said, 35 voice sessions, and voice is constantly spinning out frames, and it actually works on a well-tuned professional level 8 access point. Again, it's not your father's Wi-Fi.
Yes, I agree. we need to move off that whole Soho level. So, yes, great. Thank you.
Yeah. So now the next part of my talk is about RF and about antennas. And I think a lot of people who work in Wi-Fi are IP experts, Ethernet experts, but maybe not RF experts. And conversely, the people who are RF experts who like build GSM and 3G networks usually are not really good at IP. But really the difficult thing is RF. And that's a bit of a black art because in normal IP networking, we can plug in our Wireshark or Ethereal or what have you and sniff the packets and see exactly what's going on a wire. And we can do it to a certain degree with RF, but we really don't know what everything is happening in the spectrum. While Wireshark can be configured to decode 802.11 packets over the air, they can't tell you what's going on with a microwave oven or the cordless phone or anything else that's going on that could be interfering with the spectrum. And a spectrum analyzer can of course give you a better view of that. You can start to see what's happening, but the amount of people in the world who can really understand what's going on in the spectrum analysis in 2.4 and 5 gigahertz is pretty low. And again, most of the people who do understand that don't understand IP networking. So obviously it's a bit of a rare skill to know both. But so the result is that most people in the Wi-Fi business really don't understand RF to a super high professional level. And that includes the manufacturers of the products. And that's why up till now, most all Wi-Fi access points have used these simple omni-stick antennas. And they haven't taken advantage of a more advanced antenna technology. And also the same for the antenna manufacturers. They never paid attention to the Wi-Fi market very much. They just cranked out these cheap, low-cost omni-stick antennas that suffer, as I said earlier, from the fact that you can't load up a lot of users, and their job is to present all the electromagnetic radiation in that spectrum to the radio, whether it's good or it's bad. So as Wi-Fi moved into more professional outdoor networks, the antenna manufacturers slowly started to react. They built sector antennas. They built cross-polarized and circular polarized antennas, which have a big improvement over the vertically polarized, especially when we talk about passing through walls and trees and things like that. And by the way, 3G went through the same process. 3G antennas at first were not cross-polarized; they were singularly polarized, and 3G performance indoors. And we know it is still bad now, but it was much worse when it first started until they started using cross-polarized antennas. So cross-polarization and circular polarization is one of the important steps to making Wi-Fi more successful by allowing it to pass through objects better. Then comes the problem that you mentioned, that the 2.4 is cooked. It's overused. We all know the adage that there's only 3 non-overlapping channels in 2.4, and it suffers from neighbor interference. Well, there has always been a way around that through an active antenna that's controlled by a chip and can do filtering. But those kinds of things have always been expensive and rare and not really used by a lot of people. So along came a company that came up with some innovative ideas and developed a passive antenna that can filter out neighbor interference, that can filter out multipath distortion, and that can basically combine fragmented packets into a whole packet before it gets presented to the radio. But that wasn't where they stopped. They additionally realized one of the main problems in any type of wireless, whether it's Wi-Fi, WiMAX, or GSM or 3G, is that if one antenna out there is going to miss a lot of packets, 2 antennas devoted to a radio, I don't want to say it doubles the chance of receiving the packet, but it increases it. And 3 antennas was more. And 4, 5, 6, 7, 8, 9, 10, the more antennas you have, the better the odds are that you're going to receive a packet. And by the way, this is one of the number one benefits to 802.11n, MIMO, is not just that we're combining all the reflections into one signal, and not just that we're going to get the sexy increase in throughput to 100 megabits or whatever it is. The number one value is that you've increased the number of antennas to at least 3, and thus you have a much better chance of receiving the packet. In other words, the link can be more reliable. So this company is called Samso Height, and I think you'll share the link with on your website. So it's SAMSOSAHITE, Samso Height.
We will have the link in there as well. Can I get you to back up just for a second? And you mentioned in the past an active antenna and kind of said, it was there. You want to give a little more background on active antennas versus this new passive antenna?
Well, I don't want to give too much background because I never paid it much attention either, because it simply isn't a practical antenna to use in real networking. It's just that where you have an antenna that has an intelligence built into a chip that controls the antenna and receives all the signal from the antenna and filters out the noise and basically engineers the stream of information coming through the radio chip or coming to the radio chip into a nice clean signal. That's been possible for a long time. I'm sure I think it's probably developed by the military, like most all RF applications are. And since it has to be a powered device that's controlled by a chip, it's simply not practical in Wi-Fi networking.
Thank you. And so on to Samso Height. Is that how you pronounce it?
Yes. Well, that's how I pronounce it, anyways.
Okay, that works.
They started out as an ISP in Long Beach, California. And they ran into the same problems you were saying, that this 2.4 spectrum is just way overloaded, and I get so much interference I can't get anything done. And they happened to have access to some really brilliant people, including the guy who designed the radios for the Mars rover at NASA, at JPL there, including a 40-year military RF designer. A lot of really talented experts came together, and manufacturing experts, and they put together extremely high quality antenna that incorporated 8 separate dipoles inside of one enclosure in a 180-degree sector antenna. Or if you put 2 of them together, you have a 360 Omni with 16 antennas inside one simple small enclosure. So right there, and these are cross-polarized dipoles, you've dramatically increased the ability for this device to receive packets from clients. And the reason polarization matters is that as we're a mobile world now and our devices get smaller and smaller, we're constantly moving, especially in the case of BlackBerries and iPhones and such, that the signal is reaching the access point at multiple polarizations. And if you have a vertically polarized antenna, you're not going to receive a lot of the packets that are intended for you. And even if you're a cross-polarized antenna, if there's only one cross-polarized antenna instead of 4, you're also a bit limited in your ability to receive the packets. By having 4 cross-polarized, which is 8 dipoles, you dramatically increase the ability to receive a packet. And this is still connecting to one end connector on the bottom of the antenna, which goes to one radio. So it's not MIMO we're talking about here, but it is, in effect, giving you the same benefit as MIMO, or the most important benefit of MIMO, by having multiple antennas and increasing the odds of receiving the packet.
Can you mix these with MIMO and have multiple of these in each MIMO spot?
Yeah, I'll get to that. But a couple other important points is that take a step back, and what's the most difficult thing in Wi-Fi is not so much the interference; it's the fact that the clients are so weak. The access points can be very strong, and 4 watts of emitted isotropic emitted radiated power. I think the EIRP is the FCC standard. Whereas the devices are less than a watt, well, much less than a watt of power. And so the clients I'm talking about. So a client can see an access point a mile away, but the access point can't see the client that far away in most cases. So, in fact, pretty much every case, a mile is too far for a weak little client to get back. So by these antennas being able to listen better, we can greatly extend the range of Wi-Fi. In fact, I've gotten over here in Europe, we use kilometers. I've gotten a kilometer distance with my laptop from an access point connected and sending packets through, which most people think is impossible without, and this is with no help at all in the laptop. It's no USB stick or no extra power or anything like that. The other part of it is that since these antennas are filtering out the noise, the radio is more efficient. And like I said earlier, most radios and access points are rejecting a lot of packets. They reject all the noise they see. And that takes up time and processing power on the radio chip. So if we eliminate the noise through filtering, now the chip can work faster and be more efficient, and it doesn't have to issue so many retransmits. And the obvious result is the throughput is higher. So on signals that are very weak, in normal cases, where we might get a megabit per second of throughput at maximum, now with this technology, you're getting 15 megabits of throughput on the same connection. I
totally agree with you on the concept there, and that makes perfect sense. If there is less noise, obviously you're going to get a better signal-noise ratio, higher throughput. How can a passive antenna with all those multiple antennas feeding together do the filtering to clean up the noise part?
Okay, here's where some of the magic comes in. I'll first talk about the neighbor interference. Each frequency has a unique impedance. And if you build into the board of the antenna that these antennas are mounted on the ability to do impedance mismatching, you can then filter out all the signal that is not of the same impedance that your intended frequency is. And so the antenna samples the packets coming from the radio side, and so it knows, therefore, without even being programmed, it just learns what channel the radio is on. And it tunes itself to eliminate the other channels through impedance mismatching. That's one part of it.
Is that on a per channel 1 versus 6 basis, or is that on a frequency like it's going to not match 2.4 to 2.5 gig?
No, it's per channel. Per channel I'm talking about. So so effectively, neighbor channel interference is pretty much eliminated
by the antenna itself.
By the antenna itself before it even gets to the radio. Yeah, and
it does that dynamically in the sense that you attach the antenna to an AP, and if the AP is on channel 6, it will match just for channel 6.
Yes, and it will filter out channel 5 through 1 and 7 through 12 or 13.
I got to get one of these to play with.
Another part of it is the multipath distortion, which is common in Wi-Fi, pre-11n Wi-Fi, of course I'm talking about. And there's actually 2 networks running on the board of this antenna. And so it can detect when signals are coming in out of phase and moves the bad signal off onto the secondary network where it gets terminated. And so that also doesn't get presented to the radio.
Okay, you got me intrigued now.
When building these antennas, they found that doing all these things, having the 8 antennas on the board and doing the impedance mismatching and the multiple networks and so on, they found that they had to be super, super precise in all the engineering they made. They found that the little holes that they drilled in the board to put the mountings on things, if they were off by 1/100,000th of an inch, it had an effect on the performance of the antenna. We also discovered the end connector that's all professional level antennas have. There's a lot of different types you can buy on the market. And when I say market, I'm talking about Taiwan and China, basically, obviously, where all these things are made. There's cheap ones, and there's medium price ones, and there's expensive ones, and everything in between. And the expensive ones have the internal conductor where the pin connects is actually made of gold. And the result is obviously the more you pay, the better performance it is. So this antenna is engineered to the highest level of performance. And that's the only negative thing there is about this antenna is due to all these engineering and high quality and gold tips. It's the most expensive antenna out there compared to what people are used to paying for a Wi-Fi antenna. But when you sit down and do the math, especially if you're operating a network with paying customers on it, if you can reach further and get more customers and give them better service, better throughput, the antenna usually pays for itself. And the other result is you need less nodes because the range is longer with these, so you need less wireless nodes throughout a city or an area to provide service.
And is this specifically for outdoor, or I'm assuming you can also use these in indoor environments? Yeah.
Yes, in fact, they did a special project for a customer who had a large manufacturing facility, which obviously is filled with metal, which has a negative impact on any type of wireless. And they could not get Wi-Fi to work no matter what they tried. And they came in and put these antennas in, and all of a sudden Wi-Fi was working just as if you were in an ordinary office with cubicles around. It's a great performance everywhere. Now, they have not yet seen that as a major market for them, so they haven't productized that indoor antenna. But the outdoor rated antennas can be used indoors, and they're selling all over the world now. So,
well, you mentioned some extra price on this. I mean, is it like 100 times more expensive than normal antennas? What's kind of a price range we might be looking at?
Several times more. It could be $200 or $300, depending on how you buy it, where you buy it. Or I think maybe the MSRP is $400 US for each antenna, and then they discount it. Like most products get discounted.
Well, that's expensive, but that's not crazy expensive. I mean, especially if it does stuff.
Yeah, and you just have to judge if it's worth it to you. And most people when they do price, and it's the same thing with back to mesh networking. Those mesh nodes that have 2, 4, 6 radios in them, obviously going to cost more than an ordinary access point with one radio. And so you do an apples to apples comparison. You say, oh, that's too expensive. But when you consider the total cost of the solution, especially the larger the network you build, the more it becomes important. And you consider on the mesh side that there's no wires connected to the nodes, and that obviously saves a lot of cost. Then that's when you say, okay, it is worth it to spend this money.
So the official name for these new antennas is called frequency splitting receptacle?
Fractional summing reception device, FSRD.
Fractional summing receptacle. Okay. I obviously we have to do some more research.
Fractional summing reception device. I think that, not receptacle, reception. But yeah, you can see on the website and read up about it, and of course you can send them email and they'll give you a lot more information. And they're, like I said, they're based in California, and I think both in Long Beach and Huntington Beach there. And
have you mixed these two things we've talked about, the mesh and the new antennas, together?
Yes, absolutely. And the obvious results, as I've discussed, you get the better range performance, and you end up needing less mesh nodes to cover, for instance, a square mile. And so the cost of deploying the network can actually be lower, and of course you get better penetration, reach more clients. Now the other aspect is in the backhaul network, 5 gigahertz, which is commonly used for backhaul and outdoor mesh networking, does not pass through trees very well. And outdoors you find trees, so it's a big problem backhauling in various cities and places where the link has to go through a tree. The higher frequency signal does not pass through water well, and trees have water in them, and that's the result. Now, what we found with these devices, I think, I'm going to explain this in a non-scientific manner, but I hope it's understood, that the trees and the water inside the trees diffuses the signal, and the fractional summing reception device kind of puts it together into a clean signal to present to the radio. So if you have these on both sides of the link, you have a much better performance through trees, both in the 2.4, but more importantly in the 5 gigahertz, which suffers more from this problem.
Well, that was great. Well, Matt, I appreciate your time today sharing the technology on mesh with Strix, and we'll put their links in the show notes, as well as information on the FSR. I'm going to have to learn that new acronym there.
FRSD.
FRSD.
FSRD. I keep screwing up myself. Fractional summing reception device. FSRD. Yeah.
And we'll put those notes in the show notes. What's your Twitter handle?
Matt Holdrege, my name. Although I'm a bit old school, I kind of use Twitter for entertainment more than reality, the real important thing. So email is the best way to reach me, Matt, M-A-T-T, @strixsystems.com, or a private email, which is not really that private, is Holdrege, my name, @gmail.com.
Well, thanks for your time today, and we'll put the notes up in the show notes and share this, and hopefully we'll learn more. And if there's other information, feel free to contact me again, and we'll get you back on the show. Thanks for your time.
Thank you, Keith.
Well, I'd like to thank Matt for his time and effort spent speaking with us and sharing some information about mesh networking and the new antenna technology that he mentioned. Both of those websites and links are in the show notes. And if you'd like to suggest any other topic, in fact, Matt was introduced to me via one of our listeners and that said that it might be a good guy to have online. And I think that Matt's done a great job. So if you have any ideas, feel free to add those, and we'll talk to you next week. Thank you.
Wireless LAN Weekly, a podcast focused on the needs of wireless LAN professionals. We look forward to your feedback. Please leave your comments at the bottom of the show notes, or email feedback on the show can be sent to feedback@wirelesslanprofessionals.com. If you'd like to leave a voicemail feedback, just call 24/7 and leave a message at 1-801-481-9018. Until next time, this has been another production of wirelesslanprofessionals.com, a place to educate, inform, entertain, and inspire.